Section 3.4, the title is Velocity and Other Rates of Change. We've talked quite a bit about this already, and we're going to take it a little deeper. We'll start off with S of t, reminding you that that is typically given as a position equation with distance with respect to time. From physics, you might already have heard this term, displacement. It's a net change, and that is final position minus initial position gives you your displacement. It's the position at some time minus the position at another time. T1 would be your initial, where you start at time, and T2 would be your ending time. So you subtract those, you get your displacement. An example of that would be if you started out on a number line. Let's say you started out at, let's say here's 0, 1, 2. You started out at 2, and that's where you started. So you're moving along this number line, and then after, 4 or 5 seconds, you end up at -3. So your displacement is your ending time, or your ending position, your ending position, -3, minus your initial position, 2. And so your displacement is going to be -5. And that just means that you ended up 5 units to the left of where you started. So displacement does have a sign, positive or negative. So as we move on, we have an average rate of change. Always, that just means algebra 1. And that would be like S of 2 minus S of T2 minus S of T1 over T2 minus T1. That's just like y2 minus y1 over x2 minus x1. That's a slope. And that is displacement over change in time. The numerator is just displacement. And so your average rate of change is always going to be displacement over change in time. So that's something that you should definitely know. Instantaneous rates of change. Instantaneous rate of change was always calculus, and that's a derivative. So when you hear instantaneous rate of change, you automatically should be thinking derivative. And of course, there's your definition of a derivative, the ADQ. So let's take a look at example 1. We are given a position equation. S of t equals 2t cubed minus 6t. S of t is measured in feet. T is measured in seconds. So that's really important that you understand that we're measuring in feet and seconds, and it's a good idea to underline that so that when you get done, you make sure that you are using the correct units, because that will be very important. Part A, we're asked to find the average velocity. So the average velocity is going to be, and that's on the interval from 1 to 4 seconds. So we want to do S of 4 minus S of 1 all over 4 minus 1. S of 4, when you plug it in, you get 4 cubed. 64 times 2 is 128 minus 24. And 128 minus 24 is going to be 104 minus S of 1. And S of 1 would be -4. And that's all going to be over 3. That ends up being 108 over 3, which is 36, and that will be feet per second. That's my average rate of change from t equals 1 to t equals 4 seconds. So from the 1 second mark to the 4 second mark, not from the beginning. The beginning would be t equals 0. Part B, we're asked to find the instantaneous velocity at t equals 4 at 4 seconds. So the instantaneous velocity is going to be S prime of t, which is v of t, and that will be 6t squared minus 6. We want the velocity at the 4 second mark, so v of 4 is going to be 6 times 4 squared minus 6. And that will come out to be 4 squared is 16 times 6 is 96, minus 6 is 90 feet per second. That is my instantaneous velocity at t equal 4 seconds. So now we have s of t, we know is a position function based on time. The derivative ds dt, derivative of s with respect to t, s prime of t is equal to v of t, which is the velocity function based on time. Well, velocity has a direction. If the velocity is positive, if you get the velocity is a new number. If that number is positive, then, and we have a horizontal motion, then it will be moving forward, or it'll be moving to the right, or if you are like from a wall, you'd be moving away. In other words, the distance is increasing if the velocity is positive. If it's vertical motion, it's moving up. So that would mean like the distance from the ground is increasing. So the velocity is positive in those senses. If the velocity is negative, that means the particle would be moving backwards or to the left, or closer to the wall. The vertical motion would be down if the velocity is negative. Speed is always positive. It's the absolute value of velocity. So it doesn't matter which direction you're moving, up, down, left, right, forward, backward. Speed is always positive. When you are in your car, speedometer is always a positive number. So here we have a position function, s of t equals 2t cubed minus 6t. The velocity would be the derivative of that, which would be 6t squared minus 6. And it says if s of t describes horizontal motion in meters, what direction is the object traveling at 4 seconds? So I take the derivative, which is velocity, and we plug in a 4. And if you do that, you get 6 times 4 squared is 16 times 6 is 96, minus 6 is 90. So v of 4 is 90 feet per second. That's a positive number. So we know that that particle is moving to the right. It's horizontal motion, so we say it's moving to the right since v of 4 is greater than 0. What is the speed at 4 seconds? That'll be the absolute value of the velocity. The absolute value of 90 is 90. It's a positive number already. So it's 90 feet per second is the speed. And then what about at 0.5 seconds? What direction is it? Well, the velocity of 0.5 would be negative 9 halves. And that comes from putting in 1/2 for t, squaring it. Getting 1/4 times 6 is 6/4 minus 6. That would be 3 halves minus 12 halves, which is negative 9 halves. So it's negative 4.5 feet per second. Because the velocity is negative, we know the particle is moving to the left, and the speed would be the absolute value of negative 4.5, which is 4.5 feet per second. And again, speed's always positive, absolute value of velocity. So next, we're going to take a look at the second derivative of the position with respect to time. That's s double prime of t, or v prime of t, and that's the acceleration, a of t, as a function of time. In the English measurement system, acceleration due to gravity is 32 feet per second squared, or 32 feet per second. That is always a constant force of gravity. It doesn't change. In the metric system, it's 9.8 meters per second squared. And gravity will affect any object when it is, not on the ground. Well, it affects it when it's on the ground. It keeps it on the ground. But anyway, if you are having an object that is moving upward, gravity is trying to force it down, so it's going to slow the object down. You shoot something up into the air, it takes off very fast at first, or throw something in the air, it will slow down. Gravity will affect it, slowing it down. If something is dropped and falls to the ground, the object is going to speed up because gravity is helping it and pushing it down faster. One thing I want to make sure you are well aware of is A lot of people mix up acceleration. They think, a positive value for acceleration means you speed up and a negative means you're slowing down. That's not true at all. You have to wipe that out of your head. That is not true. So let's talk about what is true. When velocity and acceleration have the same sign, and I guess I didn't say that earlier, but acceleration also has a sign, a negative or a positive sign. We'll talk about that here in a sec. So if velocity and acceleration have the same sign, the object is going to be speeding up. The velocity graph will be moving away from the x-axis. So here's a situation. Here's a velocity graph, all right? And here, the velocity is a positive value because it's above the x-axis, but the acceleration, which its derivative, is a slope, and that's going to be a negative. So they don't have the same sign here. Here, the velocity is negative because it's below the x-axis. This is a velocity curve, this whole thing. And the slope is also negative. So from here, from A to B, the object is going to be speeding up because velocity and acceleration are both negative. All right, so when they have the same sign, they're speeding up. So it would be speeding up from A to B. It's also going to speed up from C to D because velocity is positive. It's above the x-axis. The slopes or acceleration are also positive. So it's speeding up from C to D. If V and T and S and T have the opposite signs, velocity and position have, velocity and acceleration have opposite signs, the object is slowing down. And the graph will be moving toward the x-axis. So here, the graph is moving toward the x-axis. Velocity and acceleration have opposite signs. Velocity positive, acceleration, the slope negative, slowing down. You can see that that would be true because think about it. Up here, the velocity might, let's say, be 10. Here, the velocity is, let's say, maybe 2, maybe 1, and then down to 0. So obviously the velocity, it's decreasing, the speed is decreasing. When you go from A to B, the velocity is 0, then it might be -1, then it might be -2. And so the speed, or absolute value velocity, would be from 1 to 2. It's increasing. So the speed's increasing from B to C. Velocity and acceleration. Velocity is negative, but acceleration, the slope is positive. They have opposite signs. It's slowing down. The graphs are moving toward the x-axis. They have opposite signs, velocity and acceleration. And again, this might be a -2 velocity. This might be a -1 and 0. Absolute values would be 2, 1, 0. It's slowing down. And then, of course, we already talked about this being speeding up. Again, velocity positive, acceleration positive, slopes are positive. Velocity, again, even before you learned any of this, you could easily see here's a velocity of maybe 1, then 2, then 3, then 4, then 5. It's getting bigger, so its speed is increasing. So again, it's speeding up from A to B and from C to D. It's slowing down from 0 to A, and it's also slowing down from B to C. So now let's take a look at this example. We have a student that walks in front of a motion detector, and it records her velocity at 1-second intervals for 36 seconds. She stores the data in her graphing calculator and uses it to generate a time velocity graph shown right here. We're supposed to describe her motion as a function of time by reading this graph and when is her speed a maximum. So on the y-axis, the y-coordinate gives her velocity at any time t on the x-axis. So at 0, her velocity is 0, so she starts from rest, and then because the velocity becomes a positive value immediately after that, she is moving to her right. All right, or you could also say she is moving away from the motion detector, depending on how it's measuring it. So she's moving to the right. She's also speeding up. Velocity and acceleration are both positive. It's moving away from the x-axis. So she starts from rest, she moves to the right, and she moves to the right the entire time the velocity is positive. So that would be from 0 to 14 seconds. During that time, she speeds up from the 0 to the 4-second mark. She is moving at a constant speed from the 4 to the 8-second mark. her velocity stays somewhere between, 4 and 5, so like 4.5 meters per second. And then from the 8 to the 14-second mark, she's slowing down. At the 14-second mark, she stops. And then she changes direction, and she is either moving left or she is moving toward the motion detector. And she's going to be speeding up from the 14-second mark until the 20-second mark, moving to the left. At the 20-second mark, she's still moving left because the velocity is negative, but she is slowing down. Her speed is slowing down. The velocity is getting up to here, and now at the 26-second mark, her velocity is 0, which means she's stopped. She remains stopped and just stands still from the 26-second mark all the way to the 32-second mark. And then from the 32-second mark, after that, she's going to be back moving to the right or moving away from the motion detector, and she is speeding up. In example 2, we have a rock thrown straight up into the air, and its position, measured in feet with respect to time in seconds, is given by S of t equals negative 16t squared plus 160t. First, we're supposed to find the average speed of the rock over the first 4 seconds. So we'll find the average velocity by taking the change in position over change in time. In other words, that's displacement. S of 4, position after 4 seconds, minus S of 0, the position where it started, over 4 minus 0. If you do the calculations, plugging in a 4 into S function, and you'll get negative 256 plus 640, subtract S of 0, which is 0, and you end up with 384 over 4, which is 96 feet per second. That's the average velocity, and since it is a positive number, it's also the average speed, 96 feet per second. If that had been negative, you would have had to change it to a positive for average speed. Part B asks you to find the instantaneous velocity at 4 seconds. So you will have to take derivative. As soon as you see instantaneous velocity, boom, derivative of position. So S prime of t, which is the velocity, is going to be 2 times negative 16 is negative 32t plus 160. And then V of 4, you simply plug in a 4, and you come up with 32 feet per second is the instantaneous velocity at the 4-second mark. Part C, how high does the rocket go? And you have to use calculus, not algebra. We know this is a parabola that opens down, which means the vertex will be its maximum height. And the maximum height occurs when the velocity reaches 0. As something goes up in the air, it's going to decrease in speed until it hits its total highest height, and then the velocity is 0, and then it starts down. And the velocity then is negative, and it speeds up as it comes down. We also know that if we graph a position equation, that the maximum height occurs at the vertex. It's also when there's a horizontal tangent to the position equation. And that horizontal tangent will occur at the vertex, of course. So we take the derivative, and we get the negative 32t plus 160, which we had already done before. We set it equal to 0. Negative 32 plus 160 equals 0. Negative 32t plus 160 equals 0. We solve, bring the 32t over here, divide by 32, you get t equal 5. So we know it reaches a maximum height when t equals 5 seconds. So the maximum height will then be S of 5, which is 400 feet. So in part D, the question is, what is the rock's speed when it is at a height of 256 feet above the ground? So S of t, which is negative 16t squared plus 160t, we want that height to be 256, and we've got to figure out at what time will it be that high. So if I take and bring these two terms over to the left, I get 16t squared, positive 16t squared minus 160t plus the 256 equals 0. If I divide all three parts by 16, in other words, multiply both sides by 1/16, you get t squared minus 10t plus 16 equals 0. That factors into t minus 2 times t minus 8 equals 0, which means at time t equals 2 seconds or t equals 8 seconds, this rock will be at a height of 256 feet above the ground. So if I want to know the velocity at that time, I simply plug a 2 into the velocity equation. And remember, the velocity equation was negative 32t plus 160. So it's going to be negative 32 times 2 plus 160. That gives me 96 feet per second. When t is 8, if you plug an 8 in, you will get negative 32 times 8 plus 160, and that comes out to be a negative 96 feet per second. That makes sense because right here, if you're at a height of 256, this is t equal 2. The slope, of course, velocity is going to be a positive slope. That's the positive 96. Over here on this side, at 8 seconds, the slope is negative 96. So then it says, that gives you the velocity equation, which we already knew. We need t when the position is, okay, so we already did all that. So we basically did what it said, so let's move on to part E. What is the acceleration of the rock? What is the acceleration of the rock? Well, v of t is negative 32t plus 160, so a of t is going to be simply v prime of t, which is negative 32 feet per second squared. And of course, we know that's the acceleration due to gravity on Earth. F, when does the rock hit the ground? And the question says calculus. The answer is no. We don't need calculus for that. When the rock hits the ground, we know that the position of the rock is 0. So we simply set the position equation S of t equal to 0. And that comes out to be 0 and 10. If you plug in a 0 into the position equation, which is way up here, you get 0. And if you plug a 10 in, you will also get 0. You can factor that out. Right here, we already have it factored. T equals 0 will make it 0, and so will t equal 10 to make this all equal 0. So 0 and 10 are the times when the rock is on the ground, so that's starting and it ends at 10 seconds. What is the speed when the rock hits the ground? Well, we need to know the velocity at the 10-second mark. So you put in negative 32 times 10 seconds in for t plus 160. That's our velocity equation that we had found earlier, right up here, negative 32t plus 160. So negative 32 times 10 plus 160 is going to end up being negative 160 feet per second. So the speed of the rock when it hits the ground traveling 160 feet per second.